In the last class, we started the branch group in 8085 microprocessor instruction set, and there we discussed about JMP address and J conditional address instruction. The next instruction under this group that I am going to discuss is PCHL. So PCHL, this instruction, what it does, it loads the content of HL pair in the program counter. So whatever is the content of HL pair, if the content of HL pair is 6050H, then after execution of this instruction PCHL, your program counter will get loaded with 6050H and the program execution will start from this address, as the program counter gives the address of the instruction which is going to be fetched. So the program will get started from this instruction. Now flags affected, obviously no flags will get affected, since it is just a copy and paste operation. That is, the content of HL pair is getting copied and it is getting stored in the program counter, so no flags will get affected. No arithmetic or logical operation is taking place here. Number of bytes, as you can see, there is no extra hexadecimal number mentioned along with this instruction, so number of bytes will be 1. Machine cycle, it will take only one machine cycle, and that too for opcode fetch, because after fetching and decoding it, microprocessor will get to know it has to store the content of HL pair in the program counter, and both the HL pair register and the program counter register, they are within the microprocessor, so it does not have to perform any extra machine cycles to execute this instruction. So one machine cycle is enough, but it is an exceptional cases. It is an exceptional case because here its opcode fetch machine cycle will need 6 T states. Generally we have seen that opcode fetch machine cycle needs 4 T states, but here opcode fetch machine cycle needs 6 T states. Addressing mode, the addressing mode is registered addressing mode, because here the operand is stored in the HL register pair, and from HL register pair it will get copied and stored in the program counter. So both program counter and HL register pair, they are registered, so the addressing mode is registered addressing mode for this instruction. Next instruction under branch group is call address. For example, I'll give you an example how this instruction is executed. So let me tell you what this instruction does. So call address means whenever you are writing any program, whenever there is any main program and you want any sub program or a subroutine program to get executed a number of times, you use call instruction for that. So what happens whenever you are writing a main program and in that you use call instruction like call address, what will happen, the main program execution will get suspended there, and whatever address is mentioned along with the call, that address will get stored in the program counter, and from and the program execution will get started from the address which is stored in the program counter. That is the address mentioned along with the call address. So it is used to transfer program control to a sub-program or subroutine, which is a group of instructions. This instruction pushes this instruction pushes the program counter content onto the stack and locates the given address and loads the given address into the program counter. So how it does, let me show you. So what this instruction will do, it will store the address, the next address which is after this instruction. It will store that address in the stack memory, and whatever address is mentioned along with call instruction, that address will get stored in the program counter. So again I am repeating what are the two jobs that this instruction is going to perform. First job is like the main program, wherever the call instruction is written, the next instruction after the call, the address of that instruction, the address of the next instruction after the call, that address will get stored in the stack memory, and whatever address is mentioned along with the call instruction, that address will get stored in the program counter. So these two jobs will get performed. So how these jobs are getting performed, let me take an example. Suppose before execution of the instruction, suppose we have the main program. So how the program is written, we have instructions, and for each instruction there is an address mentioned. So like for call instruction, call 2000H, the address mentioned is 6000H. Now this call 2000H, how many byte instruction is this? It is a 3 byte instruction, because 1 byte for opcode and the remaining 2 bytes for the address mentioned along with the instruction. So it is a 3 byte instruction. So whenever you are going to write 6000H, call 2000H, 6000H is where where this instruction is going to get stored. So it is going to occupy 3 bytes. So if it is the memory and this is the 6000H address, so first the opcode of the call will get stored. First memory location will that is first memory location having the address 6000H, as here 6000H is mentioned. So there the opcode of the call instruction will get stored, and the remaining 2 memory locations will be used for storing the address mentioned along with the call instruction, that is 2000H. How it will get stored? First the lower byte of the address, and the next memory location will be used for storing the higher byte of the address. In this way 3 bytes of the memory location will get used. 3 byte memory locations will be used to store this call instruction. Now 6000H call, so this is how the call instruction is being stored in the memory. Now after and at that point, before execution of the program, let us suppose the stack pointer is having the content 3000 and the program counter, obviously because the call instruction is being executed, so the program counter will show 6000H address, because program counter will show that address where the instruction, which instruction is being executed upon. So the stack pointer is showing 3000. Now let me tell you the concept. Stack memory is again a separate memory. It is a read-write memory where any data can be temporarily stored, or can be temporarily stored and can be it can be taken out from the stack. It is basically handled by the microprocessor only. So what is happening? So initially stack pointer is showing 3000H. So here I have made the stack memory. Let me be more clear. Sorry. So yes, here I have made the stack memory. This is the stack memory. As you can see, this is the stack memory. The stack pointer is showing the address 3000H. So stack pointer will hold that address to which it is pointing recently. Again I am repeating, stack pointer will hold that address to which it is pointing recently. So here, as you can see, before the execution of the program, stack pointer is pointing to the address 3000H. So the stack pointer is having the address 3000H. Now after execution of call instruction, call address instruction, here the address is 2000H. What will happen? First, the next instruction to the call, the address of that instruction will get stored in the stack memory. So what is the next instruction address? As I have told you, that call will occupy 3 bytes. So 6000, 6001, 6002. So it is going to occupy 3 byte memory locations for complete storage. So 6003H is actually storing the next instruction to the call. So 6003 will get stored in the stack memory. So here I have shown what will happen. Initially the stack pointer was pointing to 3000H, so stack pointer will get decremented by 1, and there the higher byte of the address will get stored. Again the stack pointer will get decremented by 1, and there the lower byte of the address will get stored. So in this way 6003 has been stored in the stack memory. Now since 6003 has been stored in the stack memory, and recently the stack pointer is pointing to the address 2FFEH, So here you can see the stack pointer is having the address 2FFE. H is representing the hexadecimal format, and the address that is mentioned along with the call instruction, that will get stored in the program counter. So after execution of, again I am repeating, what will happen after execution of call instruction, whatever address is mentioned along with the call instruction, that will get stored in the program counter, and the next instruction address to the call, next instruction to the call, the address of that instruction will get stored in the stack memory. So and how you going to calculate the next instruction address? By calculating how many bytes your call instruction will occupy. So as I told you, call instruction will occupy only 3 bytes. So taking up the 3 bytes, the next address will get stored in the stack memory. Now flags affected, no flags will get affected as no arithmetic or logical operation is being taken place here. Number of bytes, how many bytes of instruction? Obviously 3 bytes, 1 byte I have already told you, 1 byte for opcode and remaining 2 bytes for the address. Machine cycle, how many machine cycles will be used? 5 machine cycles. How? First machine cycle for opcode fetch. So after fetching the opcode and decoding it, microprocessor will get to know that it has to store the address, next instruction address, in the stack memory, and it has to store the address mentioned along with the call in the program counter. So first opcode fetch and the second machine cycle will be used for storing the lower byte of the address. Which address? Next instruction address, lower byte of the next instruction address in the stack memory. So second machine cycle is used for memory writing. Third machine cycle will be used for writing the higher byte of that address in the stack. So in this way the next instruction address has been written into the stack. Now fourth machine cycle will be used for reading the lower byte of the address from the memory. Which address? The address that is mentioned along with call, since this address is present inside the memory. So the fourth machine cycle will be used for memory read purpose, that is reading the lower byte of the address. And fifth machine cycle will be used for reading the higher byte of the address. Once the address reaches the microprocessor will store that address in the program counter, and the program execution will start from that loaded address. So all total 5 machine cycles. T states, how many T states? Obviously opcode fetch machine cycle needs 4 T states, memory write needs 3, memory write needs 3, memory read needs 3, memory read needs 3. So all total how many T states? 16 T states. So 16 T states. Addressing mode, now it can be 2 types of addressing mode. First, immediate, because here the address is working as the operand, as this instruction stores the address in the program counter. So here the address is working as the operand, so you can say that the addressing mode is immediate addressing mode. So it is the immediate addressing mode, or it can be registered indirect addressing mode also. Now next instruction is call conditional address. Call conditional address is same as the call address, just the difference is this, कि if the condition gets satisfied, only then the call conditional address will get implemented. Means what will happen, let me tell you in terms of the machine cycles how it will get executed. Just 1 minute. I told you that in call conditional call address the number of T states is 16. Sorry, there is a correction. The number of T states is not 16, it is 18, because here obviously it will need 5 machine cycles, one for opcode fetch and 2 for memory read and 2 for memory write. But here the opcode fetch machine cycle will need 6 T states. So all total 18 states. This is a little bit correction, you just make it. I miscorrectly said previously that it will need 16 T states, but it is actually 18 T states. Similarly, in call conditional address, let me show you the example with the machine cycle, how this thing is going to get implemented. So call conditional address, first machine cycle will be used for fetching the opcode. call condition, the opcode of this call conditional address. So the format is call conditional address, or you can see here I have written actually how it is written: CC address, CNC address, CZ address. So CC address means, C means call, C represents the condition, and ADDR represents the address. And what CC address actually says, call the subroutine, means the call program will only get implemented if the carry status is 1. The status of the carry flag is 1. CNC address means, here I have shown CNC address, these all are call conditional addresses. This is just the format. Actually, how you going to write the call conditional address instructions in this way that I have written here. Like CNC address means call instruction will get implemented only if the status of the carry flag is 0. So similarly, all the call conditional instructions I have written here, like CZ, call instruction will get implemented only if the 0 flag is set. Similarly, okay. Now what will happen? First machine cycle will be used for fetching the opcode. After fetching the opcode and decoding it, microprocessor will get to know that it has to store the address mentioned along with the call in the program counter, and it has to store the address, next instruction address, in the stack memory. So the second machine cycle will be used for storing the lower byte, storing the higher byte of the next instruction address in the stack memory. So the second machine cycle is used for memory write. Again I am repeating, first machine cycle is used for opcode fetch, and the second machine cycle is used for writing the higher byte of the next instruction address in the stack memory. So while in the second machine cycle, microprocessor will also check whether the condition is fulfilled or not. If the condition is fulfilled, means the call will get implemented and further machine cycles will get executed. But if the if the condition is not fulfilled, means the call instruction will not get executed and it will stop within 2 machine cycles only. Now if the condition is fulfilled, what will happen? Next machine cycle will be used for storing the lower byte of the address in the memory, in the stack memory, that is memory write. Now fourth machine cycle will be used for reading the lower byte of the address, from the memory, which address? The address that is mentioned along with call. And the fifth machine cycle will be used for reading the higher byte of the address from the memory, which address? The address that is mentioned along with the call. So in this way, in 5 machine cycles, the whole call instruction will get executed only if the condition is fulfilled, and if the condition is not fulfilled, then it will get ended within 2 machine cycles. So here I have written also 5 if the condition is true, and else 2. Now number of T states, obviously if the condition gets fulfilled, the number of T states will be 18, because opcode fetch will need 6, memory write, memory read will need 3 T states individually. Similarly, if the condition does not get fulfilled, then it will need only 2 machine cycles. So opcode fetch needs 6 T states, memory write needs 3 T states, so all total 9 T states. Addressing mode, immediate addressing mode or register indirect addressing mode. Immediate, why? Because here the address is working as the operand here, because address is going to get stored in the program counter. So again, concluding, what call instruction will do, whether it is call conditional or simple call instruction, the 2 main jobs of the call instruction are: first, storing the next instruction address in the stack memory, and then what will happen in the next job will be storing the address mentioned along with the call in the program counter. So I'm ending this class here. Thank you.